Hi, I am Masayasu Aotani and I am an associate professor at Kyoto University in Japan. I have a BS in chemistry from Kyoto University, a PhD in mathematics from UC Berkeley, and an EDD in second language acquisition from Temple University. The purpose of this video is to introduce the course I teach titled Modern Physics, which is actually quantum mechanics, to international students. This video is a narrative version which does not contain any formulas or equations. If you are so inclined, feel free to check my book-length lecture notes available online. The URL is http://aoitani.net/modern_physics.pdf, where M in modern and P in physics are capitalized. I think it's shown at the bottom of the screen now. Now this video is also a chance for you to meet me up close and personal, albeit virtually, before you decide to take the course. First, a short note on the course title. You know, the name of the course is in order, I think. While it is called Modern Physics, as I just said, it actually covers quantum mechanics only. It is true that a modern physics course should cover quantum mechanics and the theory of relativity at the least, but there's a simple reason why the course is modern physics and not quantum mechanics. In the planning stage of this course, there was going to be a two-course sequence, Modern Physics 1 and Modern Physics 2, where Modern Physics 1 was going to cover quantum mechanics and 2 special relativity, with a short introduction to general relativity at the end. But mainly because my specialty is much more like quantum mechanics, and also just as much because some faculty members did not like me. Actually, I have many informants to this effect. Because of those reasons, I was denied the right to teach relativity. I consider it a right, as I like teaching physics much better than my other classes, namely mathematics, statistics, and English as a foreign language. For the record again, my 2 doctorates are in mathematics and second language acquisition, which is foreign language learning and teaching. Hence, so when I say I like teaching physics better than mathematics, it may seem like, you know, saying I like a neighbor's kid better than my own, but I really mean it. Furthermore, at least as a graduate student, I had a more extensive background in physics and chemistry than mathematics. Details of my career are in a different set of videos. Search on YouTube with Masayasu Aotani as the keyword, then you'll see my personal history video and many others. Now, quantum mechanics. While special relativity explains high-speed phenomena where an object moves at near the speed of light, quantum mechanics is useful in describing or explaining microscopic phenomena. In a way, it is a refined version of Newtonian mechanics. When we are dealing with, say, a baseball, Newtonian mechanics is all that we need. However, in order to describe an electron whose size is less than 1/trillionth of that of a baseball, we need to resort to the quantum mechanical theory. Some of the oddities and attractions of quantum mechanics are as follows, just to whet your appetite. These strange predictions, assertions, or consequences, whatever you call them, of quantum mechanics are all experimentally verifiable, as odd as they may seem. 1. A physical object, like an electron, is here and not here at the same time. Differently put, it is everywhere at any given time t. 2. Particles sometimes behave like a wave. 3. The total energy of an electron in an atom can only take discrete values. So think of 1, 2, 3 as opposed to any value in the interval 0 to infinity. 4. The classical theory cannot explain laser. We need quantum mechanics. And by the way, parenthetically, we need relativity to use GPS as satellites move very fast. 5. When we observe an electron, its state after the observation is different from what it was before the observation. 6. While a baseball thrown against a wall will certainly bounce back, a part of an electron hitting a potential wall goes through the wall and appears on the other side of the wall. In fact, the development of quantum mechanics was driven by some of the above observations, which kind of defied, physicists' common sense based on Newtonian mechanics. In classical physics, we most often describe a physical system by a differential equation, and this characteristic is preserved in quantum mechanics. The beauty of quantum mechanics is that only one differential equation, called the Schrödinger equation, contains all the necessary information about a physical system. In this beginning course, we will focus on the physical systems for which the Schrödinger equation can be solved analytically and exactly, and not just numerically. This is in order to acquire a solid grasp of the basic concepts and develop a good sense of direction, so to speak, in quantum mechanics. Quantum mechanics at this level can be understood in terms of infinite dimensional matrices and vectors of unit length, where vectors represent physical states and matrices correspond to physical quantities such as the position and momentum of a particle. A course like this often starts with a minimal set of assumptions or axioms and derive everything else from them. This approach may make the presentation appear streamlined and more sophisticated. That's true. But it is harder to follow due to its higher level of abstraction. So in this course, in my course, we start with a larger set of assumptions and axioms and reduce the number of necessary assumptions only after the students become comfortable with the basics of quantum mechanics. We do so by explaining the relations and interdependencies among our initial assumptions. That's another important learning process. This popular and modern approach is more conducive to deepening the students' understanding. Finally, this course is based on a course I took from Professor Edward Witten at Princeton University and an inspiring book titled Principles of Quantum Mechanics by Professor Ramamurthy Shankar of Yale University. We will cover only a fairly small portion of the lecture notes available online. This is the same URL available online, my lecture notes. And don't be scared or warned by the level, by the advanced nature of actually many of the topics in this lecture notes, because as I just said, when I wrote this, I was going for completeness. In other words, through some materials are good through the first year of graduate study. So needless to say, since this is the first course of quantum mechanics, we will cover only, as I just said, a small portion of it. That's it for now. Thank you very much for spending time with me, and I'll see you some other time. Thank you.